Hello everyone and welcome to this new lecture. In this lecture we will discuss gradient operators. So in the last lecture we ended our lecture with a note that the first order derivatives are computed by using the gradients and the second order derivatives are computed by using the Laplacians. So the Laplacian operator and its filter we have already implemented, and we have seen how do we get the Laplacian operator or Laplacian mask using the Laplacian operator. So in this lecture we will discuss how do we get the masks for the gradient operator. So the gradient of an image is defined by del f, that is we call gradient of f, that is equal to, it is given by this array of two coefficients gx and gy. Gx is here partial derivative of f with respect to x, and gy is partial derivative of f with respect to y. So this is how we give the derivative, first order derivative of f or the gradient of f. The gradient vector points in the direction of maximum rate of change of f at coordinates x and y. So this we already know that the first order derivative gives us the rate of change of f in that particular at that particular coordinate. The magnitude of gradient is given by this, that is equal to under the root x gx square plus gy square. So this is how we give the magnitude of the gradient. This gradient's magnitude can be given by this, and the direction angle of this is given by tan inverse gy by gx. So these are two important parameters of the gradient. One is magnitude, another is direction angle, and this angle is measured from the x-axis of the image. Now, to compute these gradients, the simplest method given by the Roberts Robert, and it is Robert's cross gradient operators. So suppose we have this 3 cross 3 pixel group, right? Pixel sub image, or we can say. So if we want to compute the gradient with respect to Z5, Z5 pixel, then the gradient Gx, the gradient coefficient Gx is given by Z9 minus Z5. That means this Z9 minus Z5, and Gy is given by Z8 minus Z6. So this is the simplest form of implementation of first order partial derivative. Now, but since and this operator can be implemented by using these filter masks. So if I have this minus 1, 0, 0, and 1, then if I put it here uh, with in association with these four pixel values, then the result will be Z9 minus Z5, and the result of this will be Z8 minus Z6. So that we get the gradient in x direction and y direction, gradient components in x direction and y direction. But since the Roberts masks or Roberts this uh, first order partial derivatives have 2 cross 2 masks, so these 2 cross 2 masks do not have any center pixel, because this we have already discussed that for any mask to have a central pixel, the mask dimension should be in the O, right? It can be of 3 cross 3, it can be of 5 cross 5, but in this case it is of 2 cross 2. So another 3 cross 3 approach, another approach is given in that 3 cross 3 masks are proposed, and they are proposed by Prewitt. So they are called Prewitt's operator. So in this, what is done is the Gx is given by Z7 plus Z8 plus Z9 minus Z1 plus Z2 plus Z3. That means when we subtract the third row from, when we subtract the first row from the third row, then we get the derivative, partial derivative in x direction. This is x direction. This is third row. Third row, sum of the coefficients, sum of the pixels of third row minus sum of the pixel values of first row. That gives us the gx. And the gy is given by sum of the pixels of third column. This third column z3, z6, z9, and sum of the pixels of first column, that is z1, z4, z7. So this is how the uh, 3 cross 3 masks are given for the gradient computation. Now, these are Prewitt's gradient operators, and they can be implemented by these masks. So here we can see that the this is the mask corresponding to Gx. So here the coefficients associated to the third row are 1, and the coefficients associated to the first row are -1, and middle row coefficients are 0. So when we implement this mask on any pixel, on any 3 cross 3 subimage, then we will get the difference of sum of these coefficients minus the sum of these coefficients. So this can be implemented by this, and the y direction partial derivative can be implemented by using this mask. In this, the third column coefficients are 1, and the first column coefficients are -1, and the middle column coefficients are 0, 0, 0. So when we implement this for any pixel, then the third column coefficients from third column coefficients, the first column coefficients are subtracted. Okay. Then a slight variation was proposed by the Sobel. So a slight variation of these two equations uses a weight of 2 in the center coefficient. So what is done in Sobel operator? The weight is given to the weight is given more weight is given to the center coefficient. Why? Because the response of this operator will be assigned to the pixel associated with this center pixel. So it is good to have more weight to the center pixels. So this Sobel operator, this is the modified variation of Prewitt's operator. In this, what is done? More weight is given to the center pixel. So here the x gradient in x direction is given by this 1 2 1 -1 -2 -1. So again here the the weighted sum of third row from weighted sum of third row, the weighted sum of first row is subtracted, and for gradient in y direction, weighted sum of first column is subtracted from weighted sum of third column. Now, what is the advantage of using this Sobel operator is a weight value of 2 is used to achieve some smoothing by giving more importance to the center point, called Sobel operators. So here we give more importance to the center point, and by doing so we get smoothing in the output. Right? This is one advantage of using the Sobel operator. But the Sobel operator is computationally expensive. Why? Because here multiplication also comes into the picture. Why? Because we have to multiply the pixel value by 2. So 2 pixel values are needs to be multiplied by 2. So these are the basic operators which can be used to implement the partial derivatives in x direction and y direction. Now, by doing so, we have got the gradient components. We have achieved we have obtained the gradient components gx and gy. So these operators will give us gx and gy. But the magnitude of gradient is given by this expression, that is gx square plus gy square under the root. But since it has these squares and square root, these squares and square root are computationally expensive. So calculating the magnitude of the gradient is expensive in using this method. If we use this method, it will be computationally expensive. So an alternative approach is given in which this uh, gradient magnitude calculation, this gradient magnitude calculation is approximated by using this relation. So magnitude of del f, that is equal to absolute value of g plus absolute value of y. Now, what is the disadvantage of using this? The price paid for this advantage is that the resulting filter will not be isotropic in general. That means by using this, we have lost the isotropic nature of these operators. That means our gradient operators. This gradient operator is isotropic in nature, but by doing this, by approximating it like this, we have lost its isotropic nature. But if we use these Prewitt's operator or Sobel's operator, they are they give strong response in horizontal and or in the vertical direction. So this will give us strong response in the x direction, this will give us response in the y direction. So they are isotropic only in these two directions. So there is so and this approximation will also be isotropic in horizontal and vertical direction. So there is no harm in approximating the magnitude of gradient in this direction, but it is computationally very cheap, very attractive with respect to the previous expression, which is this one. That is quite complex or quite expensive computation. Okay. Now, since these two operators, these Prewitt's operator and Sobel's operator, they are uh, more sensitive to for the vertical and horizontal changes. So if we need to have the operators for the diagonal changes, so these 3 cross 3 masks can be generalized for strong response in the diagonal directions. So the Prewitt's operator can be generalized like this. So here these diagonal coefficients, these diagonal coefficients are 1, 1, 1, and these three corner coefficients are minus 1, minus 1, minus 1. And in this diagonal, all the coefficients are 0. So this filter, this mask will give strong response the for the edges which come in this direction, and this is the another variation which will give a strong response for the edges which come in this direction. In this direction, if we approach in this direction from minus to plus, then whichever edges will come, those edges will give strong response for this filter. Similarly, we can have Sobel operator also for the same directions, for uh, diagonal directions of the edges. So these are the approximated, or these are the modified versions of these Prewitt's and Sobel operator for the diagonal directions. Now, if we move further, then we have here one example. This is our original image, and here this is the uh, gradient in x direction. That means when we are moving in x direction, whichever edges appear, they will be highlighted in this image. So when we move in the x direction, here this edge appears, so this will be highlighted. These edges are appearing, so these are highlighted, and similarly these edges which are appearing in the direction when we move in the x direction. right? So these edges are highlighted in this, and the partial derivative in y direction, in this direction, will give us strong response for the edges which appear when we move in y direction. So when we move in y direction, we get these edges in the middle. So right, so these are the edges which we get when we move in the y direction. So this is the gradient response in y direction. This is the gradient response in x direction. That means it is the x component of the gradient, it is the y component of the gradient, and this is the gradient response, total gradient response, that is the absolute sum of these two values, absolute sum of these two values, that is this one. But here if we look at the bricks used on wall, they are quite uh, they have quite strong response. So here edges are quite clearly visible of the bricks of the on the wall. So for that, what is done is the same image is taken, and first a 5 cross 5 smoothing filter is used on over this image. So this image is smoothed by using a 5 cross 5 averaging filter, and after that the x gradient and y gradients are computed, and then their absolute values are added. So here we see that the wall, the bricks on the wall are not that strongly visible, and the major edges of the building, major edges of the building are more strongly visible. So by applying an averaging filter over the original image, we have weakened all the edges. So here we can see all the edges are quite strongly visible in this image, and here the edges are little weakly visible. But what we have achieved is these undesirable edges which were appearing due to the bricks of the wall, they are um, they have little less strong response in this output image. So this is the uh, advantage of using smoothing filter before applying the edge detection. Now this is the result of applying the diagonal filters. So if we apply the filter in this direction, then the edges which appear in this direction will give strong response. So these are the edges which will appear in this direction when we move in this direction. So they give the more strong response. And when we move in this direction, then these are the edges which will appear on the way. So these will give more strong response when we move in this direction. So these are the response of the diagonal filters. So this is how we implement gradient operators. That's it for this lecture. We will meet in the next lecture. Thank you.